Hey folks, this is Mr. Woodward. Let's talk about something called static equilibrium, the idea that something is at rest. Taking a look here, Newton's first law states that an object will remain in a state of rest or constant speed when forces on it are balanced. This is known as equilibrium. This means that the net force on the object is zero in both directions, horizontally and vertically. So if equilibrium is the idea that forces are balanced, then static equilibrium is just looking at the situation when the object is at rest. Okay, you could have a dynamic equilibrium situation where the object is moving at constant speed, but the net force is zero. But we're just going to be looking at objects that are at rest, and since they're at rest, the net force on them is zero. Continuing along, we can use the Greek letter sigma, which means sum, to show this truth in equation form. Okay, so here's sigma. So the sum of the forces in the x direction will equal zero if something is truly in static equilibrium, and the sum of the forces in the y direction will also equal zero. Okay, so here's an example. In this first picture, you've got summing the forces in the x would mean you've got 30 to the left and 30 to the right. Well, this 30 to the left would be like negative 30. The 30 to the right is like positive 30. So summing them up means negative 30 plus positive 30 is zero. And if you look at the forces in the vertical direction, 50 up and 50 down means 50 plus negative 50 also equals zero. So the forces in the x sum to zero and the forces in the y sum to zero. And similarly, in the next example, we've got new forces, but they also will add up to zero. So in the x direction, we've got 75 to the left, 75 to the right. They will sum to zero. In the y direction, we've got 50 up, 50 down. They will sum to zero. So again, forces are summing in the x direction to zero, summing in the y direction to zero. Okay, so these two objects, whatever they are both in a state of equilibrium. And if they are at rest, we can say that it's static equilibrium. But what if the forces are at angles so that each one is both horizontally and vertically directed, meaning that the force, like a force like this, is pointing vertically upwards and horizontally leftwards? Then if you break up each force into its x and y components, you will find that the sum of all the x components is zero, right? Sum of all the x components is zero, and the sum of all the y components is zero. So let's take a look at an example of that. Here we go. You are hanging a picture of Isaac Newton in your school using two cables. Okay, here's the first cable and the second cable. Okay, so you're not the best at hanging pictures. Obviously, the two cables holding it up are at different angles. If the painting has a mass of 5 kilograms and the tension in the 45-degree cable is 44 newtons, determine the tension in the 30-degree cable. So we want to know what this one is, using the idea that the sum of the forces in the x direction will have to be zero and the sum of the forces in the y direction will have to be zero. Include a free body diagram. Okay, so let's draw that. Here's the painting, and it's going to experience a force of gravity downwards. That will be equal to its mass of 5 kilograms times 9.8. That's worth 49 newtons. It will also be pulled up and to the right and up and to the left. I'm going to call this T1 and T2. T for tension. I already know that this is 44 newtons. I don't know what this one is. That's my question mark. And I know these angles. This is 45 degrees. This is 30 degrees. So there's my free body diagram. And now that I have my free body diagram, I can sum the forces in the x and sum the forces in the y. Okay, again, my goal is to figure out the value of this tension. So let's try it. First, summing the forces in the x direction, I know that they will have to sum to 0 because the object is at rest. So, which forces have x components? Well, this force has an x component, a leftward component. This force has an x component, a rightward component. This force does not have an x component, so I'm going to ignore that. Okay? So let's take a look at those specific components of T1 and T2. So T1 is pulling both upwards and leftwards. So I'm going to call this T1y and T1x. And T2 is acting upwards and rightwards. So this will be zooming in T1y, T2y. And this would be T2x, okay? So summing the forces in the x means that I've got T2's x component plus T1's x component, but that's going to be a negative value because it's pointing to the left. And they will have to equal 0. All right, now I've got to figure out how to find these x components, okay? So let's take a look at T2, the triangle that T2x is forming, okay? So here's the triangle right here, okay? And I want to find this leg of the triangle, okay? I know this leg already is 44 newtons. So I need to relate this leg, which is the adjacent leg, to this top leg, which is the hypotenuse. And the relationship between adjacent and hypotenuse is cosine. So I'm going to do this. T2 is 44 newtons. And the adjacent leg of that will be 44 newtons times the cosine of 45 degrees, okay? Similarly, for T1, T1 is unknown, so I'm just going to call it T1, and its x component is the cosine of 30 degrees. So I'm talking about this part here, right? And let me help you out by making that triangle a little bit more deliberate here. So here's the triangle for the x component. Okay, I'm looking for this leg, which is the adjacent, and I'm going to relate it to this leg here, which is the hypotenuse. Okay, so same setup, right? Adjacent and hypotenuse are the two that I'm relating. I'm going to relate them through cosine. And let me spell that out a little bit more clearly, because when I did it the first time, it probably wasn't super clear. I can say that the cosine of 30 degrees is going to be equal to the adjacent leg divided by the hypotenuse, right? Cosine is adjacent over hypotenuse. And I want to find the adjacent leg. That's my unknown. So if I multiply both sides by hypotenuse, these go away, right? And I get that the adjacent leg is equal to the hypotenuse times cosine 30. And that is the expression that I used here. T1 cosine 30. Again, the negative means it's just acting to the left. All right, setting that equal to 0. So yeah, I'll have 44 newtons times the cosine of 45 degrees is then equal to T1 cosine 30. Dividing both sides by cosine 30. This goes away. I get that T1 equals 35.9 newtons. And I figured it out. I figured out the tension in this cable. What if I sum the forces in the y direction instead? Would I get the same answer? Let's find out. So let's go back, sum the forces in the y. Clean up our drawing here. Okay. All right. Now, summing the forces in the y, setting that equal to 0. Here's my next approach, okay? Summing the forces in the y now will involve this force. It has a y component. It will involve this force because it has a y component. And it will involve this force because it also has a y component. So it will involve 3 forces. So what would that expression look like? Well, it's going to be T1's y component plus T2's y component plus negative of the force of gravity will be equal to 0. Gravity is pointing down. All right, T1's y component is now T1 sine 30 degrees. Plus T2's y component is T2 times sine of 45. Well, I already know that T2 is 44 newtons times the sine of 45 degrees. And then plus negative 49 newtons, because I already know the force of gravity is 49, setting that equal to 0. Okay, then doing some algebra on that. I would, move the 49 over to the right side. I would subtract 44 times sine 45, and I would get that T1 equals 35.8 newtons. And that's super close to what I got before. Before I got that T1 is 35.9 newtons. So probably just a rounding error somewhere. Okay. So either summing the forces in the x or summing the forces in the y will get you the same answer. It's just a strategic difference on whether you want to work with 3 forces, which is what's required when you're summing the forces in the y, or working with 2 forces, which is what's required when you're summing the forces in the x.